Can I have your attention, please? Welcome, everyone. Our next speaker is Yoshinori Matsunobu, and he will be speaking about Rocksdb storage engine for Mysql. Please give him a warm applause.
Hello? Good. So I'm Yoshinori. So I'm a database production engineer at Facebook. And I'm also leading a project called Myrox, which is our Facebook's new project to create a new storage engine for MySQL. So let me talk about our Facebook's background at first. So we are, at Facebook, we are very heavy MySQL users. So we heavily use InnoDB. I'm not allowed to talk about number of servers, but we use a lot of MySQL servers at Facebook. So we are heavy users of InnoDB. So we started InnoDB compression, started using InnoDB compression about 4 years ago. So we have optimized, added many features like online defrag to InnoDB. So, so Facebook uses many database servers, but our budget is limited. So we cannot buy an infinite number of machines. So at our scale, the efficiency, reducing the number of database servers is pretty important for us. So today's talk about Myrox, which is a Rocksdb, the LSM database engine for MySQL, is our new initiative to save space on our database servers. So this is today's agenda. At first, I'll talk about B-tree and InnoDB and its issues on disk and flash. And I'll talk about the log-structured merge trees, LSM, pros and cons. And I'll introduce Myrox and Rocksdb. And I'll cover some Rocksdb features, Myrox features, and I'll show some benchmarking results. So hardware trends and limitations. So SSD or flash, it's getting affordable. So its pricing is getting cheaper and cheaper. So it's much more affordable than 5 years ago. But MLC flash is still expensive. So TLC flash is very cheap, but it's a bit scary to use on the database servers. So on a hard disk drive, the spindle rotation speed is not improved much. So it's about 100 IOPS per drive. But space is increasing. But even though the space is increasing a lot, but like 4 terabyte or 6 terabyte per spindles, we cannot utilize all the storage space for database servers because space is, IOPS is limited. So reducing read and write IOPS is very important for database servers. So read IOPS can be reduced by having a huge cache tiers on top of the database servers, like memcache. But reducing writes is a bit harder, so because cache cannot reduce writes. So writes eventually has to return to the database. So SSD and flash, so the SSD is great for read IOPS, but the space and write endurance is limited. The space is limited, and write endurance is an issue on flash. So if you write huge amount of data to flash, then flash burns out. Then the flash can't be used anymore. So reducing space and reducing write volume is very important. So let me talk about what's the issue with the B-tree is. This is a pretty general, the B-tree structures. And here is an example of inserting some data into a B-tree index. This is a message table, the primary key message IDs. And there is an index on user IDs. And they insert into message, and the user ID called 31 or 10,000. So in this table, the user ID is inserted pretty randomly. So in this case, the data is stored in B-tree. So on the leaf blocks, the data, real user ID data is stored. But the 31 and 10,000 is pretty far are located on the very different blocks. So to store these data, databases has to read these blocks, then has to write data, then write data back to the disk. So these are the random reads and random writes. So if you, for example, if you insert n records, then in that worst case, then different random reads and random writes per index might happen. So this is many random reads and writes are involved when using a B tree. Another issue is write amplification, the write volume. Suppose, for example, changing a flag, the 1-byte flag from 0 to 1 of the user ID equal 10 or something. To do that, in InnoDB, it needs to read from data, from disk. Then caching in the buffer pool, then modifying one record, then writing the entire page. So in InnoDB, the one page size is 16 kilobyte. So writing back the 16 kilobyte to storage. So even though you modify just 1 byte, the entire 16 kilobyte page becomes dirty. So these 16 kilobyte pages has to be written to the storage. So in this case, the write amplification is 16 K. And InnoDB supports power failure protection scheme called the double write. So if the when writing data, when the power is down, so it has a mechanism to recover data. So InnoDB, actually by default, it writes data twice to storage. So the real write amplification becomes 32K, so which is huge. And the B-tree, the fragments gradually. So this is an example when inserting into message table where user ID equals 31. And suppose the user ID data is filling the leaf block. So the 31 cannot be inserted here. So in this case, the B-tree leaf pages the splits into 2. So when the splitted, the half of the B-tree pages are emptied. So it's only 50% of the space are used by applications. Then inserting 31. So in this case, the fragments about twice. So the real space increases twice. This is the worst case, but in practice, so it's very common that fragmentation increases space by 50% or even more. So the fragmentation really increases space. So this is an issue on when using Flash. So InnoDB supports compressions. We are very heavy user of the InnoDB compression. So InnoDB compression has some issues on space, from space point of view. So suppose there is a 16 kilobyte InnoDB page, and it was compressed to 5 kilobyte. So it's relatively good compression ratios. But actually, the InnoDB uses 8 kilobyte on space on the storage because it's aligned to internal kilobyte pages. So InnoDB supports multiple block sizes, but when using 4 kilobyte or 8 kilobyte, then it's aligned to 4 kilobyte orders. So even though you used only 1 or 2 kilobyte, it actually uses 4 kilobyte. If you InnoDB uses 5 kilobyte, then it actually occupies 8 kilobyte space. So Mysql 5.7 started supporting punch hole compression. It's a new scheme, but it's aligned to operating system sector size. And on modern Flash devices, the 4 kilobyte sector size is very common, not 5 and 2 bytes. So it's aligned to 4 kilobyte. So it continues to use 8 kilobyte space, which is a huge overhead. Yep. So there are lots of space and the write amplification issues on B-trees. So on the other hand, there are different interesting the database, the storage mechanism is emerging. This is called the LSM, the log structured merge. So this is Rocksdb architectures, the basic architectures. I'll describe more in the later. But there is a mem table, which is caching writes and write log files for disaster recovery purposes. Then gradually the mem table entries are flushed to a storage. And when mem tables were flushed, the file called SST, the sorted string table, is created. And gradually the files are compacted, which is called compactions. And when doing a read request, reading from multiple levels and mem tables. So this slide shows about how LSM works. Suppose inserting into message table, user ID code 31 or 99 or 10,000. These writes are going to mem table and write ahead log. When mem table gets full, it's writing to a new SST file with sorted orders. So the data is sorted. The new SST files are created. On the other hand, there are multiple existing SSTs. Then these SST files, multiple SST files are merged, then compacted, then returned to new SST files sequentially. So actually, even though you did a lot of modifications, random write, thank you. Yeah. Even though you do a lot of random writes, actually when on the LSM side, these SST files are sequentially read and written to the storage. So, and even though you do hundreds or thousands of random loads modifications, only do a couple of the sequential reads and writes on the LSM side. So this is very efficient for hard disk drive. So actually, LSM is pretty popular on the hard disk drive side. For example, HBase is a LSM database, which is very popular on the hard disk drive. And LSM handles compression better. So LSM on the SSD file, the SSD file size is much larger than the InnoDB page size. So 16 megabytes or 32 megabytes is pretty common. So here's the uncompressed, the 16 megabyte SSD file. It's compressed. So LSM compresses data. So compressed, then the new SSD file becomes 5 megabytes, for example. So, but it's not actually aligned. The alignment overhead is much smaller than InnoDB. So the OS sector size is only 4 kilobytes. So even though it's aligned, the 5 megabyte SSD file was aligned to 5 megabytes. So no alignment overhead. So alignment overhead is pretty negligible. So this is another advantage. And the LSM by nature has lots of reducing space and write amplification techniques. So it's append only. So append only means you don't need read, modify, write, and you don't need double write. And prefix key encoding, this is an interesting feature that many SSD files, LSM databases have. Suppose there is a primary key, or ID1 and ID2 and ID3, and these 4 entries have the same ID1 and ID2. So if the entire data is stored, there are many duplicates. It's wasting space. So before doing compressions, the Rocksdb or many LSM databases just trims the same prefixes, then writing these data to disk with compressions. So this saves space pretty significantly. Zero filling metadata is another interesting feature in Rocksdb. So when doing updates, Rocksdb assigns the sequential IDs. It's used for consistent reads. So sequential ID is incremented, and these IDs are using about 7 bytes. So when writing to storage in Rocksdb, so if Rocksdb decides that the sequential ID are not used by any other clients, so it converts to 0. I said 0 compresses data very well, than 1, 2, 3, 4, 5, 6, or some arbitrary integers. So zero compresses data pretty well. So this actually saves space. So uncompressed data size is not much different, but after compression, the size difference is huge. So the LSM databases like Rocksdb, it's very optimized for after compression, the space. This is a compaction algorithm of the Rocksdb, the level. So when writing data, the mem table data is first written to level 0. And level 0, after level 0 getting full, it's moved to level 1. And if after level 1 getting full, the data is moved to level 2. So there are multiple levels, and below levels have many more 10x space by default. And for each levels, data is sorted within each level. So read amplification is relatively higher. I'll talk about later. But the space amplification, it's a kind of a high school math, but the space amplification is 11%. So this is much smaller than the fragmented B-tree overhead. It's more often exceeds 50%. So the LSM database is very good for reducing space and light amplification. But nothing comes without cost. Actually, read penalty is pretty high. So this is an example that shows the InnoDB is much more efficient for reads than Rocksdb. So this is the example select. Select ID1, ID2 time from T, where ID1 equals 100, and ID2 equals 100, order by time, descending scans. And there is an index on ID1, ID2, and time. So these queries are called a coupling index range scans. So all necessary data is stored within the same index. So range scan with coupling index is done by just reading leaves sequentially. So the all necessary data is stored within the concatenated the leaf pages. So in InnoDB, technically, it's just doing a single random read IO is enough to complete requests. But Rocksdb is more complicated because there are multiple levels, and for each level, the data may exist. So in the Rocksdb side, reading from mem tables and all levels are needed, and then doing merge. So this is much higher overhead compared to InnoDB. So reducing the read penalty is very important for LSM database. The common technique to mitigate this issue is Bloom filter. So with Bloom filter, so it checks key may exist or not without reading data, and skipping read IO requests if it definitely does not exist. So Rocksdb has an API called a key may exist. For example, if level 1, level 2 returns false, then it skips reading from blocks. So in this case, the reading steps was reduced from 5 to 3, which is really efficient. So these read optimization techniques is used in Rocksdb. Another penalty is delete. This is an example. So we're inserting into T, but it's 1, 2, 3, 4, 5. And suppose you delete table T, where ID less than or equal to 4. Then the Rocksdb adds a tombstones called tombstones, delete 1, 2, 3, 4. But tombstones were not, cannot be deleted when deleting data. So suppose you select a table, select counter from T, count asterisk from T. Then even though there's only one record, it actually seeks many tombstones plus real records. So in this example, Rocksdb scans the 5 key entries to complete this request. So delete adds the tombstones, and when reading, ignoring all puts for the same keys. And tombstones cannot disappear because the same put may exist on the below levels. For example, when you override the ID1 many times, the ID1 may exist on the many levels. So when you delete after that, then the delete cannot be disappeared because delete is a marker that ID1 was removed. So the tombstones can disappear until bottom level compaction happens. So that's why there are many, when you delete huge number of records, there are many tombstones, and the select counter or range scans it becomes very expensive. So some leads need to scan lots of tombstones. This is very inefficient. So Rocksdb recently added optimizations to mitigate these issues called single delete. So if put for the same key is guaranteed to happen only once, then single delete can remove put itself. For example, the same example, but the delete can delete put and delete this myself, the single delete themselves. Then the only one the put exists. So the select count just scans only one record. So this is very efficient. And Mylox uses single delete for all secondary indexes and primary keys. So this is a short summary of the LSM. So LSM on disk and flash. My talk is pretty focused on flash, but originally the LSM was very optimized for disk because lower write penalties, but higher read penalties. So you cannot use LSM everywhere, but if the applications are really write heavy and read small, then the LSM can work better than bit.ly. LSM on flash. So main advantage is the smaller space with compressions and the lower write amplifications. These are very important for flash. The main disadvantage is higher read penalties, but LSM is, the flash is very good for reads. So in many cases, the higher read penalties can be absorbed by faster flash devices. So HBase is a distributed NoSQL LSM database. It's on top of Hadoop, the HDFS. I think this, I have not done any surveys, but I think this is, HBase is probably the most widely used LSM databases in the world right now. And at Facebook, we use HBase for Facebook messaging on disk side. But my talk is focused on Rocksdb, another LSM called Rocksdb. So Rocksdb was forked from LevelDB, key value LSM persistent store, which is embedded and can be used for many applications. Data stored locally and optimized for fast storage. So it's written by modern C and C++, which is very efficient. And LevelDB was created by Google. And Facebook forked and developed Rocksdb to use more backend services and more critical services. So we use that many backend services at Facebook, and many external large services like Pinterest or Airbnb use Rocksdb. So Mylox, this is the main focus of the talk. So Mylox is a Rocksdb storage engine for MySQL. So MySQL has a feature called pluggable storage engines, though very few external storage engines, but mostly the InnoDB is used, but it's possible. So it's possible to create a new, my own or our own the storage engines and integrate with MySQL. So we want to take both LSM advantages and MySQL features. LSM advantage means smaller space and lower write amplification. MySQL features means SQL or replication or connectors and many tools. So at Facebook, we have huge assets of the MySQL already. So there are many MySQL clients relying on MySQL features. So it's not realistic to switch to other NoSQL databases like HBase. So it takes very long time to rewrite clients. So we have taken an approach to create a new storage engine, so called Mylox. By using that, the existing clients don't have to be rewritten. So it's kind of a drop-in replacement of the InnoDB. It's fully open source, And we are working with MariaDB. Though we don't use MariaDB at Facebook, but there are many great the internal developers at MariaDB. So we are working with a guy from MariaDB. So it's getting a much development speed is pretty fast. It's getting stable. Our state is RC. So it's published to GitHub, so github.com, Facebook, MySQL 5.6. So major feature sets in MyLogs is similar feature sets as InnoDB. So we are trying to replace some of the existing InnoDB-based applications with MyLogs. So it's similar feature sets as InnoDB. So it's transactional. So Atmicity means commit and rollback. And MVCC, so non-locking reads, non-locking consistent reads. And read committed and repeatable read. So these are the major transaction isolation levels. So we decided to take a Postgres-style repeatable read approach, which is a bit different from InnoDB's repeatable read. But anyways, this isolation level is supported. And crash-safe slave and master, this is pretty important features in InnoDB. So when slave is crashed, then just restarting the instance, then slave can restart the replications. We added the same feature in Rocksdb, MyLogs. And online backup, so logical backup by MySQL dump. So it can take a consistent backup, logical backup by MySQL dump. Another important backup is binary backup. So we use extra backup in InnoDB, especially for creating a new replica. So we created a new replica by binary backup. We wanted same feature in MyLogs, so we created open source binary backup tool called mylogs_hot backup, which is also published as open source. So we provided pretty much the same feature sets to work with switch from InnoDB. So performance and efficiency in MyLogs. So we added many features to work efficiently. So InnoDB is really great database, which is very robust and which is very fast. So we have to add many features to complement the InnoDBs. So the space and write amplification it's LSM advantage. So it's I talked a lot before. So it's saved space a lot. The more important issue is reads and delete penalties. So improving read performance is very important. So we added several features. So one example is reverse order column family, so reverse order index. I'll talk about later. And single delete and prefix broom filter. For example, when running a select where ID equal 1 and time larger than something, then still can use broom filter for the equal conditions. So using broom filter for ID, then filtering records, then scanning by time. And mem comparable keys is, so when comparing records, so MyISAM or InnoDB, doing more expensive comparisons because of the case insensitive character sets to support that. So the MyLogs did a couple of optimizations to, when using case sensitive correlations, just comparing keys by single memcmp functions, which is much faster than comparing bytes in traditional ways. And optimize the statistics, we also added that. The reverse column families. The Rocksdb is great at scanning forward, but order by descending is slow. Suppose the Facebook's use case, so Facebook has a news feed, then showing messages, but it's the time series data, so the newer messages comes fast. So this means we do lots of descending scans, order by disk. But with prefix key encoding, the descending scan is really bad. So this is an example. So the ID1 and ID2 is the same. It's removed with the prefix encoding. But when doing a descending scans, so reading from the back, so 4, 3, 2, 1, but to read from the descending orders, then it has to reconstruct the prefix keys. So the extra overhead is added to that. So to mitigate these issues, we implemented reverse order the column families. So just storing the data in reverse order. Then, without reconstructing the prefix keys, just reading from the head, 4231. So actually, this is a trade-off. So with the reverse order column families, the ascending scans become slower, but the descending scan becomes faster. So we have a clear use case that some indexes are used for descending scans. So we use that feature for such a descending scan centric types of applications. The online backup. So online backup, we created that. So it clones Myrox instance while the server is running. So in the Rocksdb side, write-ahead log and data are immutable. So Rocksdb creates snapshots using Rocksdb internal APIs, then creating hard links, then copying the immutable files one by one. But the original data was updated. So when there were many huge updates, so all the hard links occupied space. So we periodically updating snapshots in order to save space or not apply to many write-ahead logs. So after that, copying files, then starting servers. So and we also support streaming backup, which is supported by extra backup too. So extra backup. So creating a backup from one server, then creating storing a backup on a remote server. So you don't need a space on local servers. So the Myrox hot backup takes care of everything. It's very similar to extra backup. So optimizer statistics. The query plans need index statistics. So Myrox stores index statistics in persistent data dictionary. So we need index statistics. Otherwise, the optimizers decides very bad query execution plans. So when creating data files, SSD files, the index cardinality statistics are also calculated and updated in Myrox. Then they are added to the SSD files. Then data dictionary is also updated. So data files are created during compaction and memtable flash. So everything is done during that. So in InnoDB, to update optimizer statistics, it reads pages randomly. So it's called an index type. So this sometimes increases the read query latencies. But no index type happens in Myrox. Okay, the performance. So my colleague, Mark Callahan, did a lot of performance testing recently in Myrox and InnoDB. So we have a tool called a Linkbench, which is very similar to the Facebook's workloads. And we measure space usage and QPS, the flash reads per query and flash writes per query, and data loading performance and query latency. And he also tested on hard disk drive. The database size. So database size this is the biggest reason why we decided to start this project. So the LSM database, Rocksdb, compressed by zlib, it's actually the space was less than half compared to compressed, the InnoDB. So the y-axis is space, and the x is time of the running benchmarks. So the Myrox space was about 400 gigabytes, and compressed InnoDB was about 900. So it about doubles the space. And the uncompressed InnoDB uses even more space. So this is clearly shows that Myrox reduces space a lot compared to InnoDB. The QPS was also great. So we added many features like a single delete or reverse column families or mem-comparable keys. So with Rocksdb zlib, the QPS was at about 30,000. And InnoDB, the compressed InnoDB was about 20,000. So the Myrox actually got the 1.5x the beta QPS. The flash reads per query. So this shows how many disk reads, the reads from flash per executing a query. So there are cache. So the many data is cached. So when hitting a cache, then skipping the reads from a storage. So the Myrox space was about half compared to a compressed InnoDB. This means a smaller space. The smaller space means the cache hit rate becomes improved. So that's why the disk read frequency per query was the smallest when using a Rocksdb. The flash writes per query, the write amplification, this was the impressive numbers. So from IOStat and from flash device, these results are a bit different because flash does the internal write operations called garbage collections, so which was not reported by IOStat. So InnoDB was, the Rocksdb was about 10x the smaller than the InnoDB. So this is the benefit of the using LSM. So data loading, the migration performance. So this is the time of some of the simulated the databases. So dumping from a running the fragmented the InnoDB index, then reloading to a InnoDB or Myrox by Mysql dump pipe the Mysql command. So InnoDB to InnoDB, the logical copy completed about the 6 hours and 7 minutes. So the size was, after loading data, the index was not fragmented. So the space was reduced a bit. On the other hand, on the Myrox side, the load finished in the 4 hours and 20 minutes. So it's relatively, the update speed is faster in the LSM side. This shows that. The query latency. The query latency is also important because latency is affecting the user experiences. So this is the cumulative response times. So number of queries is the vertical ones, then the x ones is query latencies. So InnoDB was a bit faster, but the 2x Rocksdb. 2x Myrox means since the Myrox space becomes half, so we decided to run the same size of the Myrox instance on the same spec servers, where the single InnoDB is running servers or the 2x Myrox running on the same servers. So we just consolidated more Myrox instances and measures performance. The cumulative response times was not, surprisingly, not so bad when using flash devices. So finally, Mark also tested on the hard disk drive. The hard disk drive is highly depending on the write workloads, but this shows that the QPS was pretty good on the Myrox side. Because if you do many random writes, then hard disk drive is really bad for random seeks. So the LSM doesn't do so frequently on the, about the random writes. So this optimizes space, the overhead. So so far we have proved that Myrox works really good, but there are many limitations. So Myrox is relatively newer project, but InnoDB is very robust. It's the most popular transactional database in MySQL. So it has many features, and Myrox misses lots of features actually. So we don't support the online DDL or foreign keys or spatial index or full text index yet. So we have plans to add that, but actually on the, we have not supported yet. And InnoDB supports next key locking, which is needed to make statement replication work. Now the Myrox doesn't support that. So because it's a bit complex to add that features. So we decided to use a row-based binary logging, so with, without supporting next key lock. So this is a feature limitation. So when using Myrox, you need to use the row-based binary logging. And full durability with XA means InnoDB flash log at TRX commit equal 1 is not supported yet. Actually, we rely on the slaves. So the single database is not fully durable. So when losing some database instance, then just recover from other instances or other master or slaves. This is pretty similar to Hadoop's HDFS approaches. So just relying on other the replicas. So we heavily rely on MySQL replications, but we have some plans to add full durability features. We don't support direct in Rocksdb yet. And as I described before, so either order by desk or ascending is slow. And all modifications of the running transactions are kept in memory. So when start transactions and modifying a huge number of records, then every modification is kept in memory. So which is you can't do that. So we have some special options for bulk loading. So load data in file. So we optimized for that to work. But on the general workloads, it's recommended to use short transactions right now. Okay, so this is summary. So MyRocs is pretty important project for us. So efficiency is very important at Facebook. So to us, the saving space by half is a really big deal for us. So there are trade-offs across space and light and read amplifications. And LSM reduces space and light, but increases read. So there are many read penalties. So we started the MyRocs project to take advantage of the LSM properties. So, and all MyRocs source codes, and including backup tools, are open sourced. So we don't have enterprise versions. So this is not our business model. So we open sourced everything. So you can download the MyRocs now, and you can try that. So under feedbacks, so we maintain issues on the GitHub issues. So if you see any problems, then just file an issue on that GitHub. But please don't take that Facebook is going to fully replace InnoDB with MyRocs. So there are trade-offs, and there are many applications of Facebook that are really read heavy, and it's not practical to replace with LSM databases. So we continue to use InnoDB, and we will start using MyRocs for some types of applications. But we will use both. And InnoDB is a very great database, general purpose database. And actually, I will have MyRocs more detailed talk in April, which is Percon Live, the Percon Data Conference. I have a tutorial, 3-hour tutorial, and I'll talk more in depth about MyRocs at that conference. And finally, we are hiring at Facebook. So we hire the production engineers in MySQL or many other databases. And we also hire the engineering team. We hire people. So if you are interested, feel free to talk to us. Thank you.
Thank you very much for your talk. Are there any questions?
Hello, what is the percentage of replacement of InnoDB with MyRocs?
Could you say that again? Sorry.
Percentage of replacement of InnoDB with MyRocs in Facebook.
The question was replacing InnoDB with MyRocs?
How many of existing information is replacement from InnoDB with MyRocs?
So as I talked during the slides, so LSM databases is optimized for light-heavy workloads, or read small the workloads. So if on very read-heavy applications, so it's not practical to replace with MyRocs. So we are trying to replace on the light-heavy applications or the space-constrained applications.
Are there any other questions?
Yeah.
Could you raise your hand, please? Over there.
Yeah, I heard that you support snapshot isolation. So it means that if you want to get serialization of transaction, or statement-based replication, basically, you need to lock the reads. Do you have any idea of the impact of locking every rows for reads?
So the question was the statement-based replications. So how we complement the statement replication. That's your question?
Plan to support serial isolation.
So actually, at Facebook, we are using row-based binary logging. So that's why we decided not to spend resources, engineering efforts to support the next key locking. So, but this is our reason. But I know that there are many people, external people, still rely on the statement-based binary logging. So we may add that feature in the later. But next key locking means it needs extra locking, so which will definitely hurt performance. So this is trade-off. But we have not decided yet, but we may consider definitely.
Thank you.
More questions? No? Okay, thank you very much indeed.
Thank you.